For assignment number 3, we're going to be exploring special right triangles and how we can use patterns in order to find missing sides of right triangles instead of using Pythagorean theorem. So what's a special right triangle? There's two different types. We're going to look at one of the types today. It involves a pattern in order to find missing sides, and unlike Pythagorean theorem, all you need is one side of the triangle in order to find the other two missing sides, because you're just going to use your pattern to find the missing sides. So your warm-up here for 1 and 2, your job is to look at this figure here where you have an original square and it's being dilated, meaning it's increasing in size, and you see 3 new squares. So your goal is to find the length of the diagonal of each square, and hopefully as you notice a pattern to find that length of the diagonal, you can eventually do it without any work. So the goal is to find the measure of a 12 by 12 square, the diagonal of that square without any work noticing the pattern, and then we're going to find the angle measures in the second part using the triangle sum theorem. So essentially right now we're trying to explore the pattern that's involved in special right triangles. So if you want to stop the tape and try the warm-up and then restart the tape to see if you got the same answer that I did. Here we go. So for this first smaller square, if I count the units, it's a 1 by 1. The next square over is a 2 by 2. The third square is a 4 by 4. And then the last square is an 8 by 8. So you'll notice that our goal is to find the diagonal of every single square. So this diagonal here, since I know a square has 4 right angles, it creates a triangle, in fact a right triangle, and therefore if you're given 2 sides of a right triangle, you could find the third missing side using what I'm going to fill in the blank here at Pythagorean theorem. So if you remember Pythagorean theorem, the theorem is a squared plus b squared equals c squared. It's an equation used to find one missing side of a right triangle if you're given 2 of the sides. And for all 4 of these examples, the unknown is our hypotenuse because it's opposite the 90-degree angle. So the diagonal is always your hypotenuse, or in the equation, what you're trying to find is your c. So if you remember the 2 side lengths, which happen to match in all 4 of these pictures, it doesn't really matter what you choose as your A or your B, but in this case, since they both match, we're just going to be plugging in the same number anyway. So for this first equation, I would have 1 squared plus 1 squared, and that's equal to our unknown diagonal length, c squared. So 1 squared is 1, plus 1 squared, again, is 1, and that's equal to c squared. So if you add these, you get 2, and that's equal to c squared. And just like the notes for the assignment number 2, the opposite of squaring something is square rooting. We practice this with Pythagorean theorem. So our diagonal here is the square root of 2. It does say to simplify our root, but since 2 is prime, this is completely simplified. So the diagonal here is the square root of 2. So I'm going to write it in this picture here, the square root of 2 as my diagonal, so I could start noticing a pattern. So for the second picture, we're still using the same process, a squared plus b squared equals c squared. In fact, I'm going to write that for the last 2 pictures. Alright, so plugging in our side lengths. So I would have 2 squared plus 2 squared is equal to the diagonal, right? Which is our c, our hypotenuse squared. So this would give me 4 plus 4, which is c squared. So if I add that, I get 8, and that's equal to c squared. And then finally, take the square root of both sides. So the square root of 8, you can actually make a factor tree and simplify the square root of 8. If you made a factor tree, your final simplified root would be 2 square root of 2. So this next picture is 2 square root of 2. The third picture, plugging in 4s for the lengths, the side lengths here, 4 squared plus 4 squared equals c squared. 4 squared would be 16, plus another 16 is equal to c squared. If I add those together, I get 32 is equal to c squared, and if I take the square root of both sides, the square root of 32 can be simplified by making a factor tree. So my final value, if you simplify this, would be 4 square root of 2. So if I label this maybe starting to notice a pattern might help. When it was a 1 by 1, the diagonal was 1 root 2. When it was a 2 by 2 square, the diagonal was a 2 root 2. When it was a 4 by 4 square, the diagonal was 4 root 2. So an 8 by 8, looking at the pattern, I'm expecting to be 8 root 2. So let's double check that. So if I plug in my side lengths here, 8 squared plus 8 squared equals c squared. 8 squared is 64, plus another 64 is equal to c squared. If I add those together, I get 128 is equal to c squared. And if I take the square root of both sides, 128 does have pairs. It could be simplified. So if you do simplify it, you do get 8 square root of 2. So this final diagonal here was 8 root 2. So again, do we notice a pattern in filling in the missing diagonal? Can we find the diagonal of a 12 by 12 square? So again, when it was a 1 by 1, it was 1 root 2. When it was a 2 by 2, it was 2 root 2. When it was a 4 by 4, it was 4 root 2. And when it was an 8 by 8, it was 8 root 2. So again, that first number in front represents the side lengths of the square, and then all 4 diagonals also had root 2. So if it was a 12 by 12, the diagonal would be 12 root 2. So the second part here is to find the missing angles of the triangles created. So I'm just going to draw one of the triangles. I'll pull out this picture here. So this was 1, 1, and then root 2. So if I had to classify, since it has 2 congruent sides, this would be, and I'm going to add tick marks here because they're the same, this would be an isosceles triangle. Every isosceles triangle has 2 congruent sides, and therefore it has 2 congruent angles. So I could find the missing angles by using the triangle sum theorem. And the triangle sum theorem says all 3 angles of a triangle add up to 180. So if you already know that your triangle has 90 degrees, the 2 missing angles there, if all 3 have to add up to 180, and you already have 90, you have 90 left over to split evenly. So if you take 90 and divide that by 2, the degrees would be 45s. So in fact, the very first, I said there's 2 different types here for special right triangles. The very first type is a 45, 45, 90 degree right triangle. And the goal is to notice a pattern in finding the missing side lengths. For instance, let's revisit the pattern. If I give you a 10 by 10 and I ask you to find the missing hypotenuse, if you look at the pattern that we just explored, you don't even have to use Pythagorean theorem. You can use the fact that the diagonal was always the side length of the square times the square root of 2. And we're also going to use this pattern in order to find a missing side length, even if you're only given one of the side lengths of the special right triangle. So I'm going to switch the screen so we could shift down to our final observation. So give me a second to shift over to the next part. All right, so in summary, one of the special right triangles is a 45, 45, 90 degree triangle, and of the 4 options, I'm going to use the most basic one that I saw. The most basic was created by a 1 by 1 square, and then we found using Pythagorean theorem that the diagonal or the hypotenuse is the square root of 2. So essentially, we're going to be using a kind of like a tic-tac-toe board to organize our information for all of these if we're asked to find a missing side length. Let me label the angle measures here, the 45 degree angles. So in the very first row, I'm going to write the degrees. So it was 45, 45, 90. I wrote them from least to greatest, so 45, 45, 90. And then in this next row, this is our known or the original special right triangle. So what do I write in these next 3 boxes? So underneath the 45 degrees, I would ask myself, what is the side length across the 45s? So directly across the 45 degree angles, the side lengths were 1s. So this is 1, 1. And what is across the 90 degree angle? If you look at the 90 degree angle, directly across is the square root of 2. So when you're given a new example, like the ones on the flip side, we're going to fill in from the picture, whatever new picture we have here, the missing 3 side lengths, and of course they will have variables. However, you will always be given 1 side length at least. So essentially what we're going to be doing is we're going to be using the known special right triangle, the original 1, 1 root 2, and we're just going to be figuring out what we're scaling it by. By that I mean we're dilating it, either larger or smaller, so the goal is to find the new scale factor. Like say if we're multiplying all 3 sides by 8, the new side lengths would be 8, 8, and then 8 root 2. So let's use this observation and try a couple examples on the next side. So I'm going to switch the screen real quick here so that we could get to the back side. Alright, for number 1, you'll notice that all of the triangles look the exact same size, like number 1 and number 2. They're not drawn to scale, but essentially this picture here is a larger version of the original right triangle, the 1, 1 root 2. So this chart here, we're going to fill in our 45, 45, 90. This is just the setup, and then something that you will hopefully memorize as you continually fill this in. The next row is always 1 root 2, the original 45, 45, 90 degree triangle. So in this new picture, our goal is to figure out the scale factor. So 45, 45, 90 is the special right triangle that I see. I know that it's 45, 45, 90 because there's a 45 degree angle there. There's a 90 degree angle where that box is, and using triangle sum theorem, the other angle there has to be 45. So 1, 1 root 2 is the original side lengths. So essentially you could think of it like having that small triangle here with 1, 1 root 2, and the one in the picture is now an enlarged version. So from this picture, we're going to fill in the final row here. So underneath the 45s in any order, you're going to write what's directly across the 45 degree angles. You could start with the left hand 45 degree angle or the right hand. If I start with this left hand, what's directly across from it? X. If I look at the right hand angle here, what's directly across from it? The 8. So again, you could have put the 8 first and then the X. They could be switched. You'll get the exact same answer because they're both across the 45 degree angles. And then what is the hypotenuse, or what's across the 90 degree angle? That would be the Y, right? Directly across the 90 is your Y value. So from here, once you have your chart filled out, you're looking at which column has just numbers. Is it the first column, the middle, or is it the last? So the first column has an X, the middle has a 1 and an 8, and the last one has a Y. So this is the column that you're looking at. So essentially what you're trying to do is you're trying to find your scale factor. You're saying, what can I multiply this original side length by in this picture? What can I multiply the original side length by to get a new side length of 8? Well, that's easy. 1 times 8 gives me 8. So essentially you're dilating the original special right triangle by a scale factor of 8. So you're multiplying all 3 sides by 8. You don't have to draw this little picture here. I'm just showing you what you're essentially doing with this chart. So we could find X and Y pretty quickly now. So X is just 1 times 8. So X is equal to 8. And then Y is 8 times root 2. So that's just 8 squared of 2. You're going to keep your answer as a simplified root. Essentially, you could have done this by using the pattern as well that we investigated in the warm-up, where we said, okay, if the side lengths of the square were 8 by 8, then the hypotenuse or the diagonal would have been 8 root 2. You could have done that without the chart as well. Alright, for number 2, I notice again that it's a 45, 45, 90 special right triangle, so I'm going to make my chart here. So 45, 45, 90. And then I know the original that we're always comparing it to has side lengths 1, 1 root 2. So if I look at my picture, I do have to fill in the final row. So what is across the 45 degree angles? It doesn't matter which one you start with, but I notice if I go across the 45s, I see an X and a Y. So I'm going to fill in X and Y, and again, you could have written Y and X, you get the same answer. And then what is the hypotenuse in this picture? What's across the 90 degree angle? That would be the 30. So from here, you're figuring out which column will help you find the scale factor. Does the first column have solely numbers? Does the middle, or does the last? This last column has only numbers, the square root of 2 and the 30, and the other two columns had variables, so you're going to use the last column. So essentially what you're doing here is you're trying to find the scale factor. What can I multiply root 2 by in order to get 30? So sometimes, unlike the last one, it's a little bit more challenging when you have to work with a root and a whole number. So you could do this with guess and check. However, if you want to create an equation, you can always create an equation like follows. So essentially what I'm trying to do with this column is figure out what can I multiply root 2 by in order to get 30. So I'm going to pick a variable. I'm going to use, instead of s for scale factor, because sometimes it looks like 5s, I'm going to use d for dilation. So root 2 times some dilation gives me a new value of 30. If I solve this, I could find my scale factor. So this is where we're practicing solving equations with roots, what we did on the very first assignment. So the opposite of multiplying root 2 would be dividing by root 2. So my scale factor is essentially 30 over root 2, but we practiced in the notes that you can't have a root in the denominator, so you're going to have to rationalize. Open up parentheses and multiply the top and bottom by whatever you see in the denominator, the square root of 2. When I multiply straight across, 30 is a whole number, root 2 is irrational, they're opposites, so you're just sticking them together as 30 square root of 2, and then the denominator or root times itself gets you back to the whole number 2. From here, I can reduce 30 halves. 30 divided by 2 is 15. So my final simplified scale factor is 15 square root of 2. So let's go back to the chart. I know that my scale factor is 15 square root of 2. So I'm multiplying all original side lengths by 15 square root of 2. So x is in the first column. X is equal to 1 times 15 root 2, so x is just 15 square root of 2, and then the y is in the second column. It's equal to, again, 1 times 15 root 2, so y is exactly the same as x, and the reason they're exactly the same is they're the side lengths of the square, if you think of the original warm-up. Alright, let me switch the screen, and let's get on to the last example. Alright, for number 3, again, I noticed that it's a 45, 45, 90 right triangle. Here's the missing 45, so I'm going to make my chart. So 45, 45, 90. The original is 1, 1, root 2, and again, this picture is just a scaled version of it. So if I look at this picture, the first two columns, I'm going to be filling out what's directly across the 45-degree angles. So there's an x, and then there's also a y. And again, x and y are always the same answer in these first two columns here for this example, because they lie in the 45-degree angles. So it doesn't matter what you write first, the x or the y. And then the hypotenuse is 16. Alright, so which column will help us find the scale factor? The first, middle, or the last? The very last column has just numbers, so I could find the scale factor using these two. So my goal is to figure out what I multiply root 2 by to get the new side length of 16. So again, this one is where you might create an equation on the side. So I'm saying root 2 times some scale factor, some dilation, gives me a new value of 16. So in order to solve, the opposite of multiplying root 2 would be dividing by root 2. So my scale factor, my dilation, is 16 over root 2. However, let me get a different color. 16 over root 2, however, we do have to rationalize because there's a root in the denominator. So let's open up parentheses and multiply the top and bottom by whatever you see in the denominator, the square root of 2. So if I multiply straight across, I notice I have 16, which is a whole number. Root 2 is irrational, so I can't combine those, so I just write it as 16 root 2. And the denominator, or root times itself, is back to the whole number 2. So from here, I can actually take 16 and divide that by 2, and that would give me 8. So 8 root 2 is my scale factor. So let's go back to the chart. We're going to be multiplying all original sides by 8 square root of 2. So x and y are in the first two columns. They're exactly the same value because they're the side lengths of the square. So it's just 1 times 8 root 2. So erase that, x and y are exactly the same, 8 squared root of 2. For the last one, the you try, go ahead and stop the video and then try this on your own and see if you get the same answer that I did. So for this last one, I'm going to be making my chart because I notice that it is a 45, 45, 90 degree triangle here. 1, 1 root 2 are the original side lengths, and again, this is just a scaled version of it, a larger version. So across the 45s, I notice that there's an x and then there's a y. So again, those are going to be exactly the same answer because they're underneath the 45 columns, because the across the 45s are the side lengths of the square. They should always be identical. So it doesn't matter which one you write first. I'm just going to put the x first. My hypotenuse is across the 90, which is 22. Which column will help me find the scale factor, first, middle, or last? That would be the last. So I'm trying to figure out what I can multiply root 2 by to get an answer of 22. So I'm going to make an equation. Root 2 times what dilation gives me an answer of 22. So to solve this, I divide by root 2. And there's my scale factor, or my dilation. However, this needs to be rationalized because there's a root in the denominator. So I'm going to open up parentheses, and I'm going to multiply by whatever I see in the denominator, the square root of 2. When I multiply straight across, 22 is a whole number, root 2 is irrational, so it's just 22 root 2, and my denominator is back to the whole number 2. Finally, I notice that I can reduce 22 divided by 2, so that gives me 11 square root of 2. So there's my scale factor. I am multiplying all of the original side lengths by 11 root 2. So if I look at x and y, they're in the first two columns, so they are just 1 times the square root of 2. So x and y are exactly the same answer, 11 square root of 2. So from here, you're just going to complete the homework and then submit both your notes and then the homework assignment on Canvas or Remind 101.